So I wanted to talk to you about the rope loop analogy for electric circuits. Now, I don't know if you've seen Derek Muller on Veritasium's video on the big misconception about electricity, I think it's called. And at the time of recording this video, that video's had 11 million views. And what happened is a lot of experts in physics and electronic engineering have responded with their own videos on YouTube. And I think that this sort of good-humoured, constructive conversation where people who think about things hard, criticize each other's ideas, I think this is a really important part of physics, and I think it's a really important part of physics education as well. So it's in that spirit that I am making this video. At the moment in the UK, the Institute of Physics is encouraging physics teachers to abandon what's called a donation model for electric circuits. These are things like, let's imagine that the battery, the charges are like lorries moving in a loop, and there's a bread factory which represents the battery, and the lorries collect bread, drive around, and then they give bread out at the supermarket. Okay, so that's a classic sort of donation analogy. Anyway, the IOP is inviting teachers to not use that and to use the rope loop model instead. So why do I care about this? Well, I have written a animated model for electric circuits that looks a little bit like a donation model at first glance, but isn't really, and I'll explain why a bit later on. And this has been used by expert physics teachers, thousands of expert physics teachers all over the world for about the last 20 years or so. So if the Institute of Physics want people to kind of abandon that and to use the rope loop instead, then they've probably got a pretty good reason for it. And because they think about things very, very hard, and they have very good people working for them, then it's something that I should take seriously, and maybe I can learn something, because before I did my PGCE, I had loads of misconceptions about electricity. I didn't understand it at all. I mean, I could answer questions, and I could give numerical answers to stuff, and that was all fine, but the underlying concepts I didn't get at all. The IOP's recent work on energy, I think, has been absolutely excellent. The idea that energy shouldn't be used to describe how or why things happen, but really to sort of answer kind of mathematical type questions about, can this thing happen, or how quickly can this thing happen? I think that's really useful. I think the language of abandoning types of energy, like electrical energy and all that sort of stuff, which I certainly used to use, which I've now abandoned, and instead talking about stores and pathways and energy being shifted, I think is really useful, and I've really tried to integrate that into my teaching. So this isn't like I'm in general having a go at the entire project. I think there's some really, really useful stuff there. But I think this the rope loop analogy is let's say a very good picture, and it's a really good picture, but it's a dangerously bad analogy. And that's a big claim. So why do I say that? So first of all, let's look at this idea of bad analogy. Well, the reason why it's a bad analogy is because for anything that is specific to electric circuits, its predictions are almost always wrong. And I'm not talking here about like my preferences or little bits of nitpicking in the physics. It's just wrong. It predicts that one thing will go up when it actually goes down. It'll predict that one thing will change when it should actually stay constant. I mean, and there's almost no part of the rope loop that correctly predicts the explicit physics of electric circuits. It works really well for predicting these deep conservation laws of the universe. So it works really well if you're talking about conservation of stuff, it's equivalent to charge or rope. It works really well if you're talking about conservation of energy. Those, of course, work brilliantly because they work for all systems. They have to work for all systems. It's also a really good picture, as I'll show, for the way that electric circuits, if you like, bring to life or exemplify those two laws, because there are lots of ways that conservation laws can can sort of show themselves in the universe, and electric circuits only work in one particular way. But as far as predictions are concerned about resistance, voltage, and the connections between resistance, voltage, and current, those are almost all wrong. That's why I say that it's bad. And why do I say it's dangerously bad? It's because it's so seductive. You so want it to work. It appears so simple, so elegant. It works so well with the generic conservation laws of conservation of stuff and conservation of energy. That's fantastic at that. It also, if you do some maths, it appears that there's this mathematical analog between the dynamic frictional force between the hand and the rope and the idea of electrical potential difference in circuits. But it turns out that that very quickly you stray into predictions that are just wrong. And those predictions are typically the ones that already play into the kind of misconceptions or half understandings that people have. So the reason why it's dangerous is because people make mistakes with it and they don't know they've made the mistakes. To them, it seems reasonable. And so what I'll do is I'll show you some excerpts from the internet, from other YouTube channels, which shows people using the rope loop in a way that they think is right, but is in fact completely wrong. What I want to do in this video then is I want to try and show why the rope loop is a really good picture. I'm going to be as generous to it as I can. I want to explain why I think it's a really bad model. And to do that, I'm going to explain some really basic but unfamiliar bits of physics about electric circuits. Then I want to tell you a little bit about the physics of the rope loop, and I want to show where those two things overlap and where they're different. I want to show you some examples of mistakes that teachers make. I want to share some ideas about why I think it's not teachers' fault that they make these mistakes. And then finally, I want to wrap up with some do's and don'ts, absolutely bomb-proof way of using the rope loop so you won't make any errors. So what makes the rope loop a good picture for an electric circuit? Well, the first thing to say is, just from a practical teaching point of view, it's really cheap, it's really easy to make, and it's this sort of really practical, active, sort of hands-on activity that is, is memorable and immediate, unlike an electric circuit, which involves all sorts of incomprehensible meters and stuff, and you can't see what's going on at all, apart from possibly a lamp lighting. So that's what's really nice about it. The key things with electric circuits is that there's something that moves and there's something that batteries run out of, and those things are different. And the rope loop is really good at distinguishing between those two things. So typically, we're going to say that the rope loop is a bit like the way charges move in an electric circuit. And we have the teacher typically acts as the battery and the student acts as the lamp, and the battery makes the charges move through the lamp, just like the teacher's hand makes the rope move through the student's hand. And the key thing is the rope just goes round and round and round. You don't ever run out of rope because it's just a loop. We can model the idea of electric current. We can say that the electric current's a bit like the speed of the rope, and if the rope's moving quickly, that's like a big current, and if the rope's moving slowly, then that's like a small current. And so we can use the rope loop to answer questions like, for example, why does the light bulb come on as soon as the circuit's connected? Well, one reason might be that the charges move very, very quickly from the battery through empty wires around to the lamp. But it turns out that isn't the case, and the rope loop shows how that doesn't need to be the case. And one thing to say then is that the rope is already there, like the rope loop already exists before it starts moving, and the charges are already there everywhere in the circuit. The rope starts to move everywhere at the same time, and even though it moves very slowly, you detect that it started moving straight away, and that's why lamps go on immediately. And each part of the rope moves at the same speed, and that's why the current is the same everywhere. And you can use it to show the shift in energy as well. You can say that the rope loop shifts energy from the chemical store in the teacher's body to the thermal store around the student's hand, because the rope acts as a pathway. In this case, the moving rope at least acts as a pathway, and this is like a mechanical working pathway. And in the same way, you can say that the battery shifts energy from its chemical store to the thermal store of the surroundings around the lamp through the pathway of the current. The current acts as a pathway, and in this case we say it works as an electrical working pathway. This pathways thing is only something you'd really introduce much later on. It's not sort of super introductory, but I'm trying to show you how this is a really good and consistent picture which ties together how we communicate ideas about energy. And even though the rope moves very slowly, it starts to shift energy as soon as it starts moving, and there isn't any sense in which the rope individually carries little bits of energy along the rope, which is one of the major objections to the donation model, which is the sort of seems to be the model that I use. Okay, so that's why I think I've captured there the reason why it's a really good picture for the inner workings of an electric circuit. Why do I say that the rope loop is a bad model, even though it's a really good picture? Well, you might have noticed in the explanation I gave for it being a really good picture was I didn't mention resistance, I didn't mention potential difference, I didn't mention how hard I was pulling the rope, and I didn't mention the connection between resistance, potential difference, and current. And in fact, I didn't make any changes to the circuit and try to explain changes either. And that's because if you try to do any of these things, then you'll make a mistake, because the rope loop outputs the wrong answer. And this is what's so bad about it, is that it's so seductive. It appears to give an answer, it gives an answer, but that answer is almost always wrong. So, for example, you think to yourself, oh, hold on, as I pull the rope loop, I feel a resistance. And if I squeeze harder, then I feel a bigger resistance. Hold on, electric circuits have resistance as well. That must be an analogue for what happens in electric circuits. They both feel resistances, okay? And then you might do some maths and you might think to yourself, there's a mathematical analogy between the dynamic frictional force of the rope moving through the hand and the potential difference across a load. I bet you forces, you might think to yourself, are a brilliant way of showing the voltage around circuits. Again, that's wrong. You might also notice that that if you squeeze harder, you'll think to yourself, oh, that means a bigger resistance. That must be how resistances behave. Then the rope, I tend to pull the rope slower. And that must say, oh, brilliant. What this rope loop does is it exemplifies the relationship between the potential difference and the current, and how increasing the resistance decreases the current. And all of these things just seem to be right. They seem to be right. But if you dig a little bit deeper, like if you actually try to use them, they appear to give the right answer, but they are just completely wrong when it comes to looking at the actual circuit itself. Now, to explain exactly what these mistakes are in a bit more detail, I think I need to say a little bit about the some physics of electric circuits that are very basic but often not really mentioned, and some physics of the actual rope loop. And then I can explain why they don't marry up anything like as well as you might think they do. I wanted to talk to you about a couple of pieces of really basic electric circuit physics that are very rarely talked about, but they're absolutely vital for understanding what goes on in electric circuits. And in order to do that, I thought I would just very quickly introduce you to the electric circuit model that I wrote. My aim of this video is not particularly to defend it, but I thought I can't think of a better way to demonstrate to you the bits of physics that I want to show. So I thought I'll just very quickly talk you through it. The key thing to note is that even though this looks like a donation model, this is actually a quite complex and quite subtle mathematical model whose output is visual. Okay, so the physics is hard baked into the code, and so it always gives the right answer, but it gives a visual output. So, for example, the visual output of current is the speed at which these little black dots move. The visual output of the potential at a point on the circuit is the amount of red stuff that each black dot has. The visual output of the rate at which energy is shifted in the bulb into the surroundings is shown by the expansion of this red energy circle. Now, the major objection that people have to this is that they say that charges don't really carry energy. And my argument, or my thought about that is, yeah, that may or may not be true, but we make all sorts of simplifications to help us with things. For example, forces are definitely not arrows, particularly arrows that are simplified in a way that they always act as pulls. Okay, that's the way that we tend to do, free body diagrams. All forces act as pulls, even if they're push forces, because it makes the diagram simpler. Now, no one kind of objects to that. It just helps us see what's going on if we do that. In the same way that we attribute energy to objects, or energy stores to objects quite happily. We'd quite happily talk about the energy store of the thermal store of the hot bucket of water. We'd quite happily talk about the gravitational store of the flying aeroplane, or the kinetic store of the thrown cricket ball. Okay, so in these cases we are attributing stores to particular objects, so there is a precedent for doing that. You could argue, for example, that gravitational stores don't really exist for the object, they exist in the field between the Earth and the object, for example. But these are just conventions, really. I don't think they say anything deep about the underlying physics. I think this is an example of what's called structural realism in the philosophy of science. This says that there is a universe out there, and it's made of various bits and bobs, electrons, masses, whatever. But what's real about the universe is the relationship between things, the mathematical relationship between things. But we're not too fussed about the particular objects themselves. So we're not too fussed about whether it's fields that store energy or the objects that store energy, because it doesn't lead to different predictions. You still get the same answers if you use them correctly. So I have a gentle defense of this way of looking at things. I don't think it goes against the physics, and I think it's just so enormously helpful to model potential with its per-charginess intact, because it really helps us with the ideas of potential difference, and it really helps us with the idea of power. Now, let me show you what happens when I change the voltage. Is if it were just a simple analog, what would happen if it was bread vans and bread is it would be only these charges right next to the battery that would suddenly get more red stuff. But if you look, as I increase the voltage, you'll see that the new potential is set up everywhere. And so one of the things that implicitly is hard-coded into this simulation is the idea that what's called the signal speed is very high. In other words, the circuit finds out about changes very, very quickly and re-establishes a new steady state very, very quickly. And this model doesn't explain how that happens, because actually that process is really quite complicated, but it just makes it happen. And so this is why I say that this model always gets the physics right. The physics is completely self-consistent. And out of, this has been viewed hundreds and hundreds of thousands of times by people who are much better at physics than me, and I never get anyone saying, oh, the physics is wrong. Okay, it just doesn't produce the wrong physics. Okay, so let me show you then what the two bits of physics that I think are not particularly well explained, and how these ultimately will connect with the rope loop. Okay, so the first thing is that batteries are designed to produce a constant voltage, but to change their current in response to a different resistance. So batteries are constant voltage providers. Watch what happens to the amount of red stuff as I change the bulb resistance. You see, I'm increasing the bulb resistance. The charges are moving slower, but the potential on this side of the circuit stays the same amount of red stuff, because the battery voltage hasn't changed. Look, if I give a low resistance, you see, the charges move quicker, but the amount of red stuff per charge stays the same. So batteries are constant voltage providers, and they're deliberately designed to be constant voltage providers, because what you want to do is to separate out the person who makes the battery from the person who makes the thing that the battery runs from. And the battery manufacturer just wants to say, I'll tell you what, as long as you don't make the battery work too hard, it'll deliver 6 volts for you. And the person who's designing a torch, or whatever it happens to be that the battery's going to run off, they don't care how it's produced. They just say, look, give me 6 volts. And so this is like really important, that batteries are designed and engineered to be constant voltage providers and to provide a different current when you change the load. So that's the first thing. The second thing is that when I increase the resistance, then the power, the rate at which energy is shifted in the lamp decreases. It doesn't go up. And I can do this by looking at this power meter. It doesn't really exist, but it's a thing that's part of the simulation. Watch, starting from a low resistance and going up to a high resistance, you can see that the power goes down and down and down and down, because the current gets smaller and smaller and smaller, but the potential difference stays the same. And because the rate at which energy is shifted in the lamp has gone down, the rate at which energy is shifted from the power supply has gone down as well. And that means the power supply is working less hard. So power supplies respond to a higher resistance, not by struggling, not by trying harder to push through the resistance, but by just giving up effectively. And there's a really good concept in magnetism, which is called reluctance, and reluctance is a sort of magnetic analog for resistance, and reluctance is a much better concept. It says that when I increase the resistance, it makes the battery reluctant to provide any current. It makes the battery reluctant to work hard. It's a bit like a teenager, getting out of bed. If you make it difficult for them to get out of bed by providing a cold room or, any other inconveniences for them, they don't go, oh, I'm going to have to struggle harder to overcome this difficulty getting out. They just go, well, I'm not going to get out of bed then. So those two ideas then, batteries are constant voltage providers, and batteries respond to an increased resistance by working less hard, not struggling harder. Now let's look at the basic physics of the rope loop. So the first thing to say is that when the rope is moving at a constant velocity, then the forces on the rope are balanced. So the teacher pulls the rope in one direction, and the student's hand pulls the rope in the other direction because of the dynamic frictional force between the hand and the rope as it slides through. If the teacher doesn't pull hard enough, then the rope is just stopped, because actually what happens in this case, the static frictional force just responds to how hard the teacher is pulling, and increases and increases and increases as the teacher pulls harder and harder until it eventually reaches some limiting value at least, and then it slips. Or they pull too hard, so that's what happens if you don't pull hard enough, the rope stopped, or if they pull too hard, it just gets quicker and quicker and quicker, and it accelerates and accelerates and accelerates. So if the student squeezes harder and saying, oh, this is a bigger resistance, the teacher has to pull harder, okay? The teacher can't choose how hard to pull, even though they might think that they can. The teacher always has to pull in a way that balances the static frictional force as the rope slides through the student's hands. And once the rope is slipping through the student's hands, the thing with dynamic frictional force is that it doesn't depend very much or in any particularly predictable way on the speed of the rope as it goes through your hands. So, let's imagine slow speed for a given squeeze, 3 newtons, fast speed, 3 newtons, medium speed, 3 newtons. The dynamic frictional force doesn't depend on the speed of the rope. So the teacher can't choose how hard to pull the rope. The teacher always has to balance whatever the the dynamic frictional force has to be based on the squeeze. But they can choose how fast to pull it. Okay, they can choose how fast to pull it, but not how hard to pull it. And this means that the teacher can't pull with a constant force if they're asking the student to change the squeeze. The teacher it's impossible to keep the pulling force constant. So if you say, oh no, I wonder what happens when you increase your squeeze to have a bigger resistance. I'm going to pull with a constant force. You can't. You have to pull harder. And equally, if you say, so students, can you each add a hand and I'll try to pull with a constant force? You can't. And you can probably see straight away that if you compare that with what happens with a real circuit, because force is meant to be this analog for voltage, this means that the battery voltage is changing the entire time because the force with which the teacher pulls has to change the whole time. So where does the physics of the rope loop overlap with the physics of an electric circuit, and where are they completely different? Well, as you'd expect, they are exactly the same for the deep conservation laws that govern all systems. So conservation of stuff, in the rope's case, conservation of rope, in the circuit's case, conservation of charge, and hence conservation of current. They work brilliantly. Conservation of energy works well as well. They're exactly analogous, again, because they're deep laws of the universe and they have to work. It just depends on how you keep track of them. But when we look at concepts that are specifically to do with electric circuits, this is when it all breaks down. For example, the analog of voltage is meant to be how the dynamic frictional force between the hand and the rope. But as we've seen, this breaks down because the teacher has to always pull with the same force as the dynamic frictional force, and this means that the battery voltage, instead of staying constant, floats up and down the whole time. Okay, so voltage doesn't work. Resistance doesn't work either, because if I squeeze harder, then the teacher finds it harder and harder to pull the rope. In other words, they struggle more to pull it, and this gives the impression that the battery has to work harder. And as we've seen, what happens to batteries when they encounter a bigger resistance is that they work less hard. So resistance doesn't work either. And what about the relationship between voltage and current? Well, resistance is voltage over current, so it basically just says for a particular component, if it's ohmic, the ratio of voltage to current stays constant. So if I increase the voltage, then I increase the current. If I decrease the potential difference across it, I decrease the current. But we've seen that for these analogies, for the rope loop, that's not the case, because the analog for the potential difference is the dynamic frictional force, and this doesn't depend on the speed of the rope. So there's no connection between the speed of the rope and the dynamic frictional force. The only thing that the teacher can do is kind of spoof it a little bit by pulling at a different rate, and they are able to do that, but they can't do it by keeping the force constant. In other words, by keeping the battery voltage constant. So conservation laws, brilliant. Anything to do with the actual workings of an electric circuit, it doesn't work at all. So what are some of the mistakes that teachers actually make? Well, what I've done is I've collected a few videos from various YouTube channels, and I wondered if you could spot the mistakes that people make when, for example, they make assumptions that when you increase resistance, the battery has to work harder, or they don't realize that by implication they're having to pull harder, and this means that the PD across the battery must have increased, whereas we know that the batteries are constant voltage providers. In the next section after this, I'm going to explain why it's not their fault. There's something deep about the way electricity is kind of visualized. There's something deep about the way the mathematics works. It's kind of inadequate. That it just pushes people into having these completely understandable misconceptions. But I wanted you to see some examples in real life.
And one last thing the teacher could do, picking on a pupil that you like, is you could ask them to hold the rope slightly tighter, and what will happen is as you pull it through, with it being a rope, you get a lot of friction, so you can talk about, well, a lot of energy has been transferred at the point where resistance increased.
Okay, now I want Catherine to hold the rope tight. If I pull, I should be able to pull it through. It's harder this time. Would you agree?
For the hand that is serving as the source, it now feels harder to cause the electrons to move through the circuit. The second hand is playing the role of a load.
Again, if you've got more people holding on to this, so imagine you and some people in your class, if you had 10 people all holding on with their hands like this, it's actually going to be really hard to pull that rope around, because the more people you have holding on to it, the more resistance there is, and then that resistance all adds up.
When you watch those videos, you might have noticed that some of the teachers were using lots of students to hold the rope, and did that make a difference? And the answer is that it's still completely wrong, but it's wrong in a slightly more interesting and subtle way. When you introduce more students or get the students to grip tightly or grip more tightly, then it's wrong because the teacher has to pull harder, and they were very explicit about that. And as we know, that implies that the battery voltage must have increased, but we know the battery voltage stays constant. So even at that level, it's just wrong. But there was an interesting one where they asked one student to squeeze harder, and one of the questions they asked, I can't remember whether it was in the clip, it asked them, how do you feel? And she said, it feels warmer. So the question is, does it feel warmer when one student squeezes it? And the answer is, well, it really depends. So here we've got two bulbs, and one bulb, let's say, represents every other student, and this bulb on the right here, this represents the student who's being asked to sort of squeeze harder. In other words, mimic a higher resistance. And let's use our power meter to see what happens. Well, at the moment, it's 3 watts worth of warming. If I increase the resistance, in other words, this by analogy is meant to be squeezing harder. So if I squeeze harder, watch what happens to the power. It actually goes down. Okay, so it actually goes down. So that's actually less warming. So it kind of predicts completely the wrong thing. Now, it's actually a little bit more subtle than that, because if when they started, they were squeezing less than the sum of all the other squeezes, if you see what I mean, then what happens is as they increase their squeeze, or as the in the real sense, as the resistance increases, the power dissipated, in other words, the warming increases up until the resistances are the same. Look, 12 ohms, 12 ohms, and then it goes down again. Okay, so it goes up and then it goes down. And this is kind of connected with what's called the maximum power theorem, which is something that you learn in at A level. So it still doesn't work when you have lots of students, and it makes the wrong answer more interesting and subtle. So why is it completely understandable for teachers to make mistakes? It's not them, it's the physics. And looking at it from a teacher's point of view, how do you go about understanding what goes on in an electric circuit, and particularly, how does the electric circuit respond to a change? Okay, so that's a big question. And what do you use to try to answer that? Well, one thing you might look at is the circuit maths, and we'll see in a second that the problem with the circuit maths is actually it doesn't specify what you think it might specify. Other things you use are like sort of helpful rules of thumb. For example, increasing the resistance tends to decrease current, okay, but also unhelpful rules of thumb that you might not realize are unhelpful. For example, increasing resistance makes it harder for current to flow. This harder idea is a very unhelpful concept. You've also got to think about, well, what's my mental model? What's my analogy for what goes on in circuits? And, for example, it might be the rope loop. And, how do I integrate that into it? And then you have this other sort of external pressure, which is, well, what are my students actually going to get tested on in exams? And I'm pretty blooming sure that it's not going to be fundamental ideas about electric circuits. So if I can get away with just teaching them some answers, that's going to be helpful as well. So there are all these sort of contradictions. There are these different levels at which you can look at it, and well, how do you reconcile them? How do you prioritize them? How do you choose which one to apply in any given situation? And that's very difficult to do. So the two things that we really do need to understand that are just have never been brought up, and I mentioned them, are that power supplies are designed and engineered to be constant voltage providers. And if you don't get that as an absolute primary principle, then you can have all sorts of apparently consistent ideas. I'll give an example of one in a second, that are just wrong. The other is that this idea of resistance is just a horrible metaphor. It's just really, really unhelpful. In the rope loop, it's quite clear that you feel a resistance if you squeeze harder. You definitely feel it. But with electricity, it's not really a resistance. What we're kind of saying is there's this property of a component which tells you the ratio of the voltage and the current, but the voltage to the current, but it doesn't tell you what the actual value of the voltage is or the actual value of the current is. But since changing the resistance tends to lead to a smaller current, that's what we observe in circuits. It's almost like it's kind of resisting the flow of current. You see, it's just a metaphor for what's going on. It's not really. It's not really a deep bit of physics within the circuit. Now, the problem with resistance is that you have all these sort of irreconcilable or very difficult to reconcile ideas. For example, the place in the circuit where energy gets shifted most is where the resistance is highest. And that's why in a simple circuit, it gets shifted most at the bulb and not in the wires. But even though that's where it gets shifted most, if I increase the resistance, then the heating goes down, not up, which is kind of contradictory, isn't it? You'd kind of expect it, if the resistance is where all the action happens, if I have more resistance, surely there's going to be more action. No, there's less action. And it becomes even more subtle and complicated when you have resistors in series where they're increasing the resistance of one, the actual outcome of what happens in that resistance depends on how it started compared with the other. So there are these sort of contradictory heuristics to do with resistance. And I've also suggested that rather than, or in addition to using this idea of resistance, we should try to use, possibly think about including the idea of reluctance. So if I increase the resistance in a circuit, this makes the battery reluctant to shift energy quickly, and it expresses this reluctance by providing a small current. So these are the reasons why I think that it's not surprising that teachers find it really hard to latch on to the right explanation at the right level. One problem is that the three equations we use to analyze simple DC circuits are not sufficient to give a unique answer to mathematical problems. The first two equations just come from the sort of universal conservation laws. So there's a conservation of stuff, which basically says current in equals current out for any point, and for simple circuits that just means the current's the same everywhere around the circuit. And then you have a conservation of energy statement, which is the power into the system equals the power out of the system, or at least the rate that energy is shifted into the system by the battery is the same as the rate that energy is shifted out of the system by the load, by the lamp, for example. This essentially says that the voltage across the load is equal to the voltage across the cell, or the voltage across the battery. Now, these conservation laws, the conservation of current and the conservation of energy, don't tell you anything about what the current is or anything about what the rate of energy shifting is. It just says that they're going to be equal once you know them. So there's a useful ratio for the behavior of a component that doesn't actually add anything, and that's where we get this idea of voltage. And this just says, well, we know there's a conservation law to do with energy, that tells us power, and there's a conservation law to do with stuff, that tells us current. So this ratio of power per current, or watts per ampere, which we take out the components of time, give us joules per coulomb. This is kind of what we mean by voltage, but we're not adding in really any additional concept. There's no extra kind of physics there. But the extra bit of physics is a useful ratio for the property of a load. And this is like the property of the actual load itself. So this is something extra. And this just says that we're kind of define this concept that we're going to call resistance, which we've already said is kind of a slightly dodgy metaphor. PD across a load divided by the current through the load. And you would have thought that those three equations were enough to uniquely define the current or the PD. But in fact, it turns out that they are not. And a little example sort of shows you this, I think, is that let's have a look at this sort of top circuit here. This says that the PD across the battery is 8 volts. I've got a 2 ohm variable resistor, and that gives me a current of 4 amp. Resistance is voltage over current, so 8 over 4 equals 2. Happy days. Okay, so that gives me this correct ratio. Now, what happens if I take this 2 ohms and I increase the resistance to 4 ohms? Well, what happens then? Well, we know that the PD across the power supply stays constant, that the battery is a constant voltage provider. So this battery provides 8 volts, so that gives us the ratio of 8 divided by 2 is 4, so the current must drop to 2 amps. But we can also look at it in a slightly different way, which is still consistent. So say, for example, we just had this heuristic that we know that if we increase the resistance, then the current must go down. Look, here's the increased resistance and the current's gone down to 3 amps. But if we don't know that the voltage must stay the same, and if we haven't been taught it explicitly, we've got no reason to believe why the voltage shouldn't increase. I mean, the rope loop kind of implicitly tells us it does increase. Then I get the same ratio. Look, 12 divided by 3 is 4. That gives me the same ratio. And in fact, I can just use sort of infinite number of different combinations of voltage and current that will give me this ratio of 4, which is the resistance. So the trouble is that unless you know that the voltage across the battery stays constant, then you can make consistent predictions using the maths and still get the answer wrong. So I think kind of deep down, this is one of the reasons why when people kind of look at the rope loop, for example, they can make these predictions that either they don't realize this suggests that the PD across the battery has increased, or that they just say, well, it's consistent with all these things that I know. So I'm perfectly happy with it. I thought we'd finish off just with some very quick do's and don'ts so that you can really use the rope loop to its maximum potential as a really good picture, but you don't accidentally stray into using it as a model for which it isn't well suited. So do's then, well, do show the two conservation laws, the conservation of stuff, the conservation of rope, which leads to the conservation of current, and the conservation of energy. and do bring to life the visualization of the internal workings of the circuit, the fact that the charges are already there, that the charges move very slowly, and that they start moving everywhere at the same time, and that any changes are reflected very quickly everywhere in the circuit. You can also explain or show, at least you can show that the rope moving quickly is the same as a big current, and the rope moving slowly is the same as a small current. And I think just doing those very simple things is just hugely useful. Things to avoid doing, where you might accidentally stray into predicting things that are wrong. Don't mention resistance. Don't mention voltage or PD. Don't use the rope loop to explain or predict any changes in the circuit, because it doesn't do that well. And always talk about how fast you're pulling, not how hard you're pulling, because this idea of effort tied to resistance is also misleading. I hope you found that video interesting and thought-provoking. If you have any comments, please leave them below. But otherwise, thank you very much indeed for watching.